Rahul and Arjun are moving into a new apartment and need to carry 20 boxes upstairs. Rahul carries 1 box at a time, but Arjun carries 4. Both completed the same task, but Rahul took much longer because he made more trips. In computer science, asking how much time an algorithm takes is called time complexity. Now, let's add a twist. Rahul uses a small backpack, while Arjun uses a huge trolley. Arjun finishes faster, but he requires a much larger trolley to do it. Rahul took longer, but he used very little extra space. This gives us 2 questions. How much time did it take? And how much extra storage did it require? These questions lead us to time complexity and space complexity. Time complexity doesn't measure actual seconds, it measures how work increases as the input becomes larger. Instead of tracking seconds, think of it like asking this simple question. If I give this algorithm twice as much work, how much harder does it have to work? Suppose you're searching for a specific book in a library. If the library has only 10 books on the shelf, finding the one you want is incredibly easy. But if it has 1,000 books, you'll spend much more time. The more books there are, the more work you have to do. Algorithms behave exactly the same. As the input size grows, running time also grows. We usually represent this input amount by a single letter, n. Whenever n increases, the algorithm has more work.
Everyone, please stand up.
Suppose Rahul has to count students. If there are 20, he counts 20 people. If there are 100, he counts 100. This is called linear time. Now let's think about storage. Imagine you're going on a trip. One person carries a small backpack, while another person carries 3 huge suitcases for the exact same destination. Both reached the destination, but one needed much more storage. Algorithms are similar. The extra memory required by an algorithm to run is called its space complexity. Some algorithms create temporary arrays, while others work using original data. Sometimes, saving time requires using more memory. Other times, saving memory means spending much more time. This is known as a time-space trade-off. In computer science, we often have to decide which resource is more important based on the specific problem we are solving. Have you noticed some mobile apps are incredibly fast but consume lots of memory, while others use very little memory but feel slow? Algorithms face the same trade-off. Let's summarize. Time complexity tells us how the amount of work grows, while space complexity tells us how much additional memory is required. Both are equally important concepts. Now we know what time and space complexity are, but here's another question. When we say an algorithm is fast, what exactly do we mean by that? How do computer scientists compare 2 algorithms without testing every possible input? The answer lies in asymptotic analysis, which we will explore in the very next video.